Hi, thanks for this opportunity. My talk today will be on Matter-Chern Simon's theory. This is an ongoing work with Shiraj, Shoparno, and Nikhil from TIFR. The reason I invite your interest is that I'll present a fully non-perturbative finite temperature solution to a non-supersymmetric, non-abelian gauge theory with vector fermions in curved space. This is fermionic Chern-Simons theory on S2 cross S1. These theories are remarkable for their demonstrated Bose-Fermi dualities, where the bosonic spectrum of the theory matches exactly with the fermionic spectrum of the theory, the free energy spectrum of the fermionic theory. Unfortunately, in the literature, these have only been worked out in flat space because the literature only explored them in the light cone gauge, in which the calculations become quite simplified. Our first goal was to reproduce the flat space calculations in an alternate choice of gauge, which was the temporal gauge, which I'll describe. And the way we do it is to set up the calculation general to all genus G Riemann manifolds. Our motivation for this enterprise is, of course, to establish Bose-Fermi duality in general genus G Riemann manifolds, possibly at finite n, but that's a long shot. So just to remind you quickly of the action of our theory, this is the Euclidean action, and here in our choice of gauge, the interaction term will not go away. Sigma, until I point out, will remain a general Riemann surface, and it's a thermal theory, so it's sigma cross S1. And the circumference of S1 would be the inverse temperature. Now to define my gauge, which is this quote-unquote temporal gauge, I choose partial 3 A3 to be 0, 3 being the temporal direction. The gauge invariance is now two-dimensional, which can then be factorized into, the UN could be factorized into a U1 to the N by simultaneously diagonalizing all the holonomy fields, UX. The final gauge fixing step is performed by setting the zero modes of A1, A2 fields with this condition. And if you look closely, that this choice is completely general for all genus G. So what this means is that I have a prescription here for you, which is completely general for all Riemann manifolds. And what it gives us is an effective action, which is completely local on the spatial submanifold. And here, what I have presented here in the slide is before the final step of gauge fixing. So here I haven't, so this is still U1 to the N invariant. And what you can see already is that the entire effective action is completely local on sigma. Okay, now let's compute some things precisely. Let's specialize to the case of the sphere. So we set G equal to 0. We integrate out the remaining gauge fields. We take the large N limit, and we obtain some simplifications. What happens is that the Vandermonde becomes simplified. It just becomes a number. The A3 fields become space independent, which means the path integral over A3 becomes an ordinary integral over its eigenvalues lambda. And we obtain this effective action, which now since we have fermions on a sphere, so we'll have spin connections, and we must expand the fermions in a basis made out of the spin-weighted spherical harmonics defined through equation 10. The Dirac operator on S2 is diagonalized by spinors Z plus minus, which are built out of these spin-weighted spherical harmonics, and they are diagonalized like this. We then expand the fermions in this basis of Z spinors, perform a Schwinger-Dyson method to obtain an equation in the self-energy, which we call the finite temperature gap equation. Now you must see that this equation 13 is a highly nonlinear equation. Sigma sub t appears on both sides of the equation. And the equation that we obtained, the corresponding equation in flat space, was this equation 15. In hindsight, it looks like we could have just guessed equation 13 from 15 by a simple replacement of this integral by a sum. However, this appearance is, this result 13 is quite non-trivial, and it took us months to actually derive 13. But now if we have the gap equation, we can solve it fully non-perturbatively in the two coupling, but at large n. And it's solved by this solution. The solution is expressed in terms of two functions, omega sub t and phi sub t. Omega sub t never appears in anything physical, not in the mass cap, not in the free energy. However, this phi sub t quantifies the mass cap. So we'll look at it closely in a moment. The reason we could obtain exact non-perturbative solution to that highly nonlinear equation was that we stumbled across some symmetrization identities in the large N limit. What are these identities? These are algebraic identities which look like calculus identities in the large N limit. We just throw some terms away in the large N limit which differ from this result. And these identities were for both omega and phi. Here. Using those identities, we can also solve the free energy. This is the regularized free energy, thermal free energy. It's a huge mess. There are lots of pieces. Parts of the elephant have been discovered, and many parts remain to be discovered and put together. I'll just talk about phi, which is important, which is physical, which quantifies the mass cap. In the flat space case, we could evaluate phi completely explicitly. It was a simple expression given by this. But on sphere, it's terribly complicated. So let's first look at the case where, on sphere with fluxes is what I mean. So let's look at the case of zero temperature because we anyway have to remove the 0-point energy. So let's look at phi 0 m0 with all the fluxes turned on to some arbitrary values and ordered in this ascending order with the renormalized mass appearing somewhere between anywhere relative to this position. We get this expression for phi 0. This expression has multiple terms, and this is valid for all fluxes depending on whether they are integer or half integer. Now, before we go on to analytics for phi t mt, let's look at some numeric comparison. So this is for some arbitrary values of fluxes and holonomies and temperature and radius. But what we see is that wherever we obtain a solution, the red curve, which is for the finite radius case, always gives a lower answer from the flat space case. And if the answer turns, if the mass is higher and higher, so it looks like that the two answers converge, which means that at high energies, the quasi-particle excitation is localized on the sphere such that it can't distinguish between a sphere and flat space, which is reasonable expectation. Okay, now let's get to phi t mt evaluated explicitly. In the case of no fluxes, it's still quite simple because it's just the flat space case piece plus two integrals, which were relatively simple to obtain. However, the moment we start turning on the fluxes, we see a mess in front of us. So with 1 unit of flux turned on, a half integer flux, we get multiple new terms. The same can be obtained for unit flux. The only difference would be that this tan hyperbolic would be replaced by a cot hyperbolic. However, if we start turning on higher fluxes, we'll get additional terms out of shifting of the poles of these fluxes of the thermal mass. And that is yet to be done. The other pieces of the action are yet to be assembled. I would like to point out some results out of this analysis. What we see here as different from the flat space case is that now our thermal effective action is no more independent of the fluxes, which means that the holonomy eigenvalues are no more quantized. And if the duality now has to work out, it has to work out in a mathematically different way. Another point is that the fermion determinant now is flux dependent. It receives contributions from all the flux sectors, and there is a sum over fluxes, which was not the case in the flat space case. And this looks quite similar to the calculations of the superconformal index. This is a non-supersymmetric non-conformal theory that we have. But there are certain sectors where we have this, we have certain sectors where the theory also becomes conformal. But I haven't commented on that. One point that might interest people here is that Shiraz and collaborators computed some S matrix in the light cone gauge in flat space and discovered some crossing symmetry properties, which were quite unusual. We hope that some first principles computation of S matrix might be possible in this choice of gauge. And that might shed some new light on those unusual crossing symmetry properties. The final point for the duality is that we haven't been able to solve for the bosons because it becomes complicated to solve in this gauge. That is work yet to be done. These were some of the references that I mentioned in my talk. Thank you.
Yeah, questions?
Yeah, in the second last slide, I think you mentioned this holonomy. But aren't the holonomy eigenvalue, maybe I'm getting you wrong, aren't the holonomy eigenvalues the flux you are taking?
Oh no, the holonomy are from the temporal direction. These are the temporal holonomies. By fluxes, I mean the fluxes of A1, A2 fields.
Oh, you're saying that thing is not quantized.
Yeah, so the holonomies, the temporal holonomies are no longer, they are no longer quantized because the sum over fluxes, or basically the sum over the gauge index, is no more trivial. The effective action now depends on the fluxes.
Is it a problem with the gauge choice, or is it
more fundamental? It's because of the fact that we are on a sphere. In flat space, with this gauge, it would still work out, and as we show in our previous paper, that the effective action is independent of the fluxes in the large volume limit, or in the flat space case.
So I just small question about the S matrix. So I mean, the unusual crossing symmetry was because there was an extra phase when they went from right when they did the crossing operation. The S matrix was not invariant. You had to add some phase in the S matrix. But is there is there any intuition why this gauge would shed light on that problem?
So there, the way that was obtained was by taking some analytic continuations. Here we believe that we might just obtain it directly without having to take those analytic continuations and defining those.
So in the flat space, this is just temporal gauge, right? Just usual temporal gauge?
In flat space, if you look at R3, but if you look at a thermal theory, then you can't set...
No, I'm saying for the S matrix.
Yes, yeah.
It'll just be the usual temporal gauge.
Yes. So you can set A3 equal to 0, for example. Oh, I just call 3 as the temporal directions.
Any other questions for Vatsal? If not, let's thank him for a nice talk again.
Thank you.